So then welcome to the third session of the theory of lattice Boltzmann, in particular of virtual fluids here. So we are going from one topic to the next topic. The thing we still want to talk about is related to interpolation methods. So this was on the schedule, and the reason for this is that the lattice Boltzmann methods, not all of them, but the one that we have in virtual fluids, is a completely Cartesian grid method, which is not good for all possible applications. So two problems, and the two problems we're going to discuss is that boundaries are usually or very often not coincident with grid points. So you need to deal with off-lattice or off-grid boundary conditions, so cut cell boundaries. This is one thing that we do in virtual fluids, and the other thing is that we need to be able to change the resolution, which we use by grid refinement. And this last lecture today is about how we deal with these two things in virtual fluids. So to both of these things, there are alternative methods that are implemented in different codes, which may have advantages or disadvantages. So this is how it's done in this code here. So we'll start with boundary conditions, and here I have to start with a little bit of basic theory. Boundary conditions. So here we start with a little bit of theory around the bounce back. Okay, not a lot of theory, but few points just to get started. The bounce back rule, which many of you will probably know. And for understanding this, I again use my characteristic diagram where we only look at one spatial dimensions, x, and the temporal dimension here, and we have here our lattice nodes. And we assume, so we would also have lattice nodes here, but they are actually not active because we have a wall in between here. So this morning I talked about staggered grids. Actually, when we come to boundary conditions, we actually observe that there are staggered grids because the boundary conditions, if we don't do anything special, they turn out to be located in between the nodes and not on the nodes. Yeah, I mean, you can implement other boundary conditions, but these are usually the ones that are put on the nodes. They are notoriously unstable, in particular for high Reynolds number flows, and because we care about high Reynolds number flows, they are not implemented in virtual fluids. Yeah, even though you find them in the books, but not in the code, not in our code. Yeah, which you can like or dislike. I don't know. So bounce back rule is so bounce back rule would implement as a wall, and this wall would, for example, go like this. We have a population that goes out of the domain, and I call this Fi, and then we have a population that goes into the domain, which I call Fi bar. So this is the opposite direction, and this is Xn. This is the location of the last node before the boundary. And now you can implement such a boundary condition, so giving Fi, if at the position of Fi bar, at the position of the node, at time t. Now, see, you remember this here is x, so this is delta x, and this here is delta t. And one thing that you may find strange is now we actually go into the boundary and we go out of the boundary, and you see this is delayed by 2 delta x, by 2 delta t. And this is potentially not what you find in other codes. You will find this in VirtualFluids, at least as one possibility in VirtualFluids. Yeah, and you may disagree with this. I know people who disagree with this. So this is actually the outgoing, so the post-collision state from the same lattice node at the time t. And because this population spends time inside the wall, we call this delayed bounce back. So there's also non-delayed bounce back, which would return just after one time step. Yeah. So the non-delayed bounce back, if I may, would go here and then return there, right? So why would you do this? So this is potentially people who are doing acoustics may disagree with this sort of boundary condition because it does not put the acoustic boundary at the correct location. There is a reason why this may have some advantages. So we get some observations, that there are some empirical observation that can also be kind of explained. Sometimes it's also different, but there was, I remember having many years ago, so my problem when I thought about this, my problem is a little bit, I haven't checked about this for a long time now. So maybe I'm talking nonsense. Yeah, but there was many years ago some discussion so that some lattice Boltzmann methods get easily unstable, and this was observed in some codes and in other codes not. And then when these codes were compared, we actually the observation was one using non-delayed bounce back, and they were less stable than when you use delayed bounce back. Yeah, but I don't really know when whether this is always the case. The thing is that this delay may be able to delete grid scale oscillations. Yeah, so very high frequency oscillations will just be cancelled by this delay. And this is in some lattice Boltzmann codes, for example, in the one that we implemented for solids, actually, where we have waves in solids, there it's very important that you use the delayed boundary condition because the non-delayed is completely unstable and the delayed is completely stable. But this may be observed to be more stable than the non-delayed version, but this is kind of a little bit empirical.
But when you look at the sketch that you made here, it will also appear as if there's no coupling between the xn node at time t0 and t0 plus this.
Yes. If you have, you mean if you have non-delayed, the blue one.
Look at the node at x0 delta t there where you have the blue arrow.
The blue, yeah.
That one, if you don't do the delay, then that one seems to be uncoupled to what is going on at the time step before. If you have the non-delay, because
yeah, so they. Okay, so there are so they couple in different modes. So actually, actually the thing is depending on what you do, yeah. So the one could cancel one type of oscillation, and the other one could cancel another type of oscillation. So there is actually a possibility that the one is good for doing one thing and the other one is better for doing another thing. Yeah, that's a possibility. So so actually this deserves more analysis than I have done. Yeah.
The delay seemed to set the wall exactly at the notes at the rightmost part of the delay. I mean, imagine the wall. The wall wouldn't be in the middle of the notes, since the reflection occurs at the notes at the right.
Okay, I don't know why. Okay, it superficially looks from the picture like this, yes. But this is not what happened. Okay, it is. That's not what's happening. I mean, if you look at the equation, they would put the boundary here. I mean, the thing. And I mean, it also makes sense because they are both of them. See, this is time and space. Yeah? If you have a static solution, then both behave exactly the same way. Yeah? If
Maybe this node is counted as fluid, not as solid at the right.
no, this is always solid. Okay, maybe you get this picture in the wrong way. So see, this here is only time. If there's a static solution, then both of them behave in the same way. So for the one, the wall cannot be in a different place than for the other. Yeah, and usually very close to the boundary, actually it is true that the populations don't change that quickly. I mean, this is also the reason why this works. Yeah. There is one reason. There's one stupid practical reason why you would like to do it this way, and the stupid practical reason is because this is for free. So if you use iso-twist, then this does what Martin likes to call implicit bounce back, and it's actually implicit delayed bounce back. So if you think about this, so it does delayed bounce back if you just skip the collision. For the solid node. So the solid node, these are the pluses here. So what does esoteric twist do? It always, in order to keep it running, it always has to reinterpret the direction in its opposite direction. So if you don't do this, then automatically in the next time step the directions get reinterpreted. Yeah. So if you do nothing, it will wait for one time step and then it will return the same way back. So you get the delayed bounce back for free. So another thing is if you want to have what is delayed bounce back? So this is actually a velocity boundary condition we're not deriving it. Yeah, we've derived too much today. I mean, we derive a few other things, but this is now very basic. I just tell you. And this is a velocity zero boundary condition, like it modeling a wall. So if the velocity that you want to impose is not zero, you can also do this here. Then you have to add something to the bounce back, which you can do with delay and without delay. So f minus I x n t plus either 2 for delayed or non-delayed is the post-collision state from before t. And now if you want to add a velocity, then what you can do is you can add the equilibrium, giving the equilibrium that you derive from the velocity of the wall and the density. So you always have to put the density into, you can either use a constant density or you can get the density from the neighboring node, yeah, different possibilities. And you also have to add, so minus the one that goes the other way and plus the one that goes backward. So both of them the velocity of the wall. So you can actually rewrite this as Fi after collision nt minus twice the weights. So here you can use the equilibrium from the BGK. Yeah, so this will give you the weights of the equilibrium function divided by CS square times the direction of the population times scalar product the velocity. Yeah, so this is a very I think it's called LED scheme. Yeah, it's a very simple adding the velocity to the bounce back and giving you a velocity boundary condition for any velocity. Yes. So we use C for when it was the velocity E. Okay, E. So C was E times the lattice velocity, kind of. Yeah. So E is just the direction. Okay. So this is pretty standard, all of this, and now we come to the point that is important for the implementation in virtual fluids. Yeah. So these kind of boundary conditions will put boundary conditions halfway or approximately halfway. If there are lattice Boltzmann guys really deep into they will say, so there is a dependency on the viscosity, but the dependency on the viscosity is very, very small for small viscosities. You know, there are different worlds of people who are studying viscose fluids with high viscosity and people who want to interested in turbulent flows with small viscosity. They have different constraints, yeah, and there are different things to optimize. So you know, if you read the book, then somebody jumps up, you know, but the distance is not really halfway, yeah, because there's a dependence on viscosity. So if you are using very low viscosity, then this dependency does not matter. Okay? If you use very high viscosity, then this dependency matters. So I guess the people coming here, most of them use low viscosity. This is why we did not add any correction to this. But you can know if you want to do something else, you do need to do something else. Okay. But anyway, now we assume that that the boundary is always in the middle between two lattice nodes, and this is in general not sufficient. Therefore, we need some interpolation, and the way we do it, and this is not the only possibility, we are using one-point interpolation bounce back. So, and for this, we need to look into our characteristic diagram in more detail. So I draw it a bit larger. Okay, maybe now I did it too large. So characteristic diagram, as always, this is x and this is t, and this is delta x and this is delta t. So now suppose, okay, let's have them like here. Now suppose there is a wall, and this wall doesn't do us the favor that it's exactly halfway in between. So somehow now we have to deal with this. So there would be something going out here, and we would also have somebody going in the opposite direction here. So we'll call this again the node xn. This here we'll call, how did I call it? I call it XA, I believe. Okay, let's call it XA. We also call this here XV, for this is the virtual node inside. And we call this distance here delta x times q. And in addition to the distance delta x times q, we also have a distance in time, which is delta t times q. And you see, this is the same. This is basically the same, yeah, because it's the same q. And this q, so now this is important because this is something that's in the code, right? This is the subgrid distance. Okay. Now, while saying this, I see that this is not absolutely correct because this is not the distance. The distance would be q times delta x, right? Because this is the fraction of the distance at which you hit the wall. For example, you could say that the directions that go in straight, yeah, so these are actually shorter than the ones that go diagonal. But what we mean by this q is the fraction of the distance that they would be moving. Yeah, so it would be 0 for the wall being directly on the node, and it would be 1 for the wall being at the next node. Right? This thing. So now we have to get to this. So we need to go to the actual boundary. And we do this by using linear interpolation. So we do all of this by linear interpolation along the characteristic. So the characteristic is this line that we follow through space and time. This is the characteristic. So, and now for Fi, so basically this again, this is Fi, and this here is Fi over bar, so the other direction. Fi at the location of the boundary, so I should probably say x boundary, Okay, because we are in one dimension, I'll skip the vector for now. XIBC, this is, this arrives after t plus q delta t, yeah, because it is at this location in time, yeah, is equal to fi xn. Okay, let's just say no vector, so I skip the vector. T. Now we have to use linear interpolation, which is the, what is it called? The okay, so you take the distance of the other side. It's, what is it called? The leverage rule. It's now linear interpolation. Yeah. So okay, yeah. So it's 1 minus q times the thing that goes the distance q plus q times what we have here, fi at the virtual node t plus delta t. So this would be the population that we have here. Okay? And this would go at the distance q and will be on the boundary. So this thing here is something that we know because this is the incoming population at this node, and the incoming population at this node is the outgoing population at this previous node. Yeah, that we can actually compute. So this fi at the virtual node at t plus delta t is equal to the post-collision state of x n and t. So that we can basically rewrite the entire thing as fix. So on the boundary as t plus q delta t is fi before the collision 1 minus q plus fi after collision x n t and q. So we can compute these two things from the one before collision and the one after collision. Okay? So now what we do next is to apply the bounce back directly on the wall. So assuming that this population here is just returned. So this means that we assume now without adding a velocity, but this is also implemented with the velocity. Yeah. So you also want to have sometimes a velocity boundary conditions that are not aligned with any grid. For example, if you have a moving tire or a moving plate, okay, so you're wind engineers, if you have a moving plate somewhere, yeah, so you want to have a velocity boundary condition, not non-zero velocity, that has that is cutting through the domain. So the opposite x bc t plus q delta t is simply fi. So we'll just do the bounce back. So we flip. That's all we do. xn and t 1 minus q plus fi after the collision xn plus t. Now the thing is, we are I apparently haven't drawn this here properly. Now we are at this location here. Maybe I also have to go back here. So we are at this location here. This is not where we want to go. We actually want to go here. But what we can do next is an interpolation from here to here, to this point, which is the right point in space, but not really the right point in time. Yeah, but let's say we care more about space than we care about time. So here we have the population of XA. So we do the interpolation between f in the opposite direction, XA, and t plus delta t, and f opposite direction that we just calculated, BC t plus q delta t. Now, the complete distance between these is 1 plus q delta x. Yeah? And now again, we have to multiply q divided by 1 plus delta x with this FA for linear interpolation, and 1 divided by q plus 1 with the other one, with f that's coming from the boundary condition. This is what linear interpolation does. So this gives us Fi in opposite direction, xn t. Now we have to calculate what this means for the combination of, maybe I leave this open and I write the other things first. So we have Fi at the position A, sorry, not A, so XA, t plus delta t. So in the next time step is q plus 1. So this means if we look at time, we get plus this delta t q divided by q plus 1. Yeah, so this is the distance that we have been moving here, plus Fi boundary condition plus t plus q delta t times 1 q plus 1. So what does this do to the time? So here this is in time t plus q delta t, and this is multiplied by 1 over q plus 1, right? So this gives us again delta t q plus 1, right? So now in this place here, we have the population at our neighbor, which we don't like. I mean, I told you previously that we use that we use isotwist, and in isotwist we don't know the neighbor to one side. So we would be lucky if we have our boundary condition on the side where we know our neighbor, but we could also have a boundary on the side where we don't know our neighbor. Now we have the problem for the boundary conditions, we apparently need to know our neighbors. And I mean, one thing that you always have to think about is when you do these things, don't introduce any exceptions. Because if you have one exception, you always have to check it. And then you have to check it all the time. And then you have to have a data structure for it. And then you actually need to know your neighbor, even though it's an exception. So you cannot allow an exception. So you're not allowed to know your neighbor. But this thing is, of course, just the post-collision at our node here, right? So we know it locally. So, and this here, this guy here, we just wrote down up there. So now we can rewrite the entire thing as being Fi over by xn t plus 2q delta t divided by q plus 1 is equal to, so now we have first this guy here, q divided by q plus 1, fi after collision, xn, and time step t. And now we have to write this guy here again by combining this 1 over q. So we have to, what we have to do is we have to multiply 1 over q plus 1 with this guys here. So this should give us fi xn plus t times 1 minus q divided by q plus 1. Okay, so this is this here, plus fi after collision, xn and t, and this is then q divided by q plus 1. Okay, did I get this right? So, actually, this is how you could implement it if it wasn't for virtual fluids. The virtual fluids uses esoteric twists. They say we are storing only one population. So we don't know. So when we know the pre-collision state, we don't know the post-collision state. Now you could say, we do it on the pre-collision state, then we do the collision, when we know the post-collision state, then okay, so this is one possibility. This is not how we implemented it. It was implemented so that we know the post-collision state. So we have to express everything in post-collision. And now this is where we use BGK. This is now where we use BGK. Because, okay, let's say maybe somebody is going to read this later, so I just write it down. So we're using esoteric twists. This saves only the post-collision state. So, what we are now going is we use an inverse, a simplified inverse single relaxation time. Operator that gives us an approximation of the pre-collision distribution giving the post-collision distribution. Okay? So how does this work? We'll have, how does BGK look like? BGK looks like this. So we get post-collision. So we don't use BGK, so it's only an approximation, Fi plus omega Fi equilibrium minus Fi. So this is what BGK does. So which we can write as omega Fi equilibrium plus 1 minus omega Fi, such that we can approximate Fi before collision, can say is something like the one after collision minus omega Fi equilibrium divided by 1 minus omega. Now, okay, again, you notice that the guys who do high viscosity things would hate this, because high viscosity would mean that omega gets close to 1, and then this doesn't work. So if somebody here happens to be interested in wind park simulation, then there are big chances that your omega will be close to 2, and then this actually works, okay? But then you see in which rate, on what side virtual fluids is optimized to. You can also implement other boundary conditions, other things if you do want to do something else, but this is now how implemented here. So the boundary condition that we apply now, okay, I should probably say something about this 2q plus delta t by q plus 1. Previously, we already said that we do not accurately put the boundary condition at the right time scale. And the reason why we get to this is that we get convergence in diffusive scaling only. And diffusive scaling means that the time step is proportional in error, or the errors in time step is proportional to the grid spacing squared. So if you have something that's so being first order in time is as good as being second order in space. Yeah? So we don't really care that much about being accurate in time as we are in being accurate in space. So we actually now assume that this is just going to be plus delta t. You are at this point. So you're not at the right time.
I mean, is delta t equals delta x in this graph? It seems so.
This doesn't matter. There's no scaling in this. Okay, so the boundary condition. I mean, whether you like it or not, I just tell you what is how it's implemented. The boundary condition is like this. So you get the new value fn at xn t plus delta t is realized as q, where the q plus 1 fi asterisk xn t plus fi minus omega after collision omega fi equilibrium divided by 1 minus omega times 1 minus q divided by q plus 1 plus fi after collision xn and t 1 over q plus 1. So the 1 by q plus 1. Is it incorrect? So here, wait. Okay, we have to see this again. See. I mean, Sunday evening I made a lot of mistakes. I think it's wrong there. Yes, it's wrong there. I mean, can we follow that it's wrong here? Wait. Because we were taking this one and we multiplied. No, we were taking. Wait, wait. Okay, I made maybe. So we were taking that one. Okay, we were taking that one, and we multiplied it by q plus 1, right? So then, okay, now I have to redo it again. Wait. One. Where were we? Is this one? So we multiplied this one. Okay, so there seems to be a q here. So if there's a q here, okay, don't use this scribbled notes to re-implement the stuff. Yeah. It's just trying to tell you how there may be mistakes I'm making here. So I guess there must be a Q here, right? Okay. You could, let me see. So if you sum up these Q, so if we have Q plus, would this actually make sense? Because we have Q. Yes, this makes sense, because we have to add up 1 minus q plus q plus q is 1 plus q divided by q plus 1. So yes, this makes sense. Good. Okay, great. So this is an implementation of an off-grid boundary condition, which is not actually completely accurate in time, but the advantage of this is that it only uses locally known information after collision. Yeah, nothing else is required.
I just have a question.
Yes.
Why, when you use like inverse reference time, like BGK, why you put like it's approximately?
Yeah, because we are not using BGK in the collision. So this is not, I mean, this is not really the pre-collision state. Yeah, but it's sufficiently accurate for the purpose of this. Please.
So like in the code, in the algorithm.
Yeah.
So we collide and push, let's say.
Yeah.
And then we apply the boundary condition, or is it like at the same time it's happening? Like when you get to the boundary ones, just have like a if or something? Apply this?
No. Okay, no. They're different. Okay, the implementation is different in the different versions. So let's say, for example, the GPU version, yeah, would do it like this. So we are processing all the nodes that are not inside the boundary. Yeah, so they are in a list and they will process all of them. Then there is a list of boundary nodes, and then we come to the boundary condition, and then all these boundary nodes are processed. Then each boundary node has a list of queues. Then we look whether this queue is in between 0 and, so we make a choice whether, we don't save one, we do not distinguish whether one node has 3 or 4 queues. So for every node that is close to a boundary, we assume that we have to save all the 26 queues. Then we go over all the 26 queues and see whether they are in between 0 and 1. And if they are in between 0 and 1, then they have a boundary there, and then we apply the boundary condition there. So this is how it's, and in the GPU version, in the CPU version, it's done a little bit different, because I think we are not going over lists then. Or do we go over lists again? Yeah, okay. We also have, so we also have lists. So who was first?
I would just like to point out, like this is why you can also approximate curved boundaries with LDM in a single node, right?
Yes, yeah.
Each link can have a different queue.
Yes, each link can have a different queue, yes.
And, I think that for people that are not familiar with LDM might be, I think that a lot of people stumble over that when we say we can approximate curved boundaries with the Cartesian grid.
Yeah, okay, so
With a certain order.
I think your mathematician will jump into your face, because you're not, you're protected by your beard. So this technically is not a curved boundary, because it does not consider the curvature. I mean, because we have also implemented a long time ago, we also implemented curved boundary. If you implement curved boundary, you really have to do a correction in the Navier-Stokes equation due to the curvature. Yeah? So then you are even an order higher. So what you're doing is you point-wise approximate the distance. Yeah? But all the time you're assuming you're not considering whether this is a flat surface or not. And this makes a difference, because you get a correction term if you have a curvature. Yeah? That you're not using. So now trouble, so from a practical point of view, yeah, because we are talking practical things usually. So should we spend, I mean, if somebody is looking for a PhD topic, come forward and do this for curved boundary. Problem being, practical problem being, mostly we don't get very, very nice geometries in the first place, and then everybody gives us STLs. Yes, so we get triangle meshes. There is no information on curvature. So if I spend my time implementing boundary conditions for curvature, which I've done in the past, and I notice there is an additional term that we have to take care of, yeah, then nobody gives me the right input. I mean, I can do this for a sphere, yeah? But usually the meshes that I get, they're all triangle and there's no curvature in it. So I don't see the point that I spend my time implementing complicated boundary conditions. And they are pretty, I mean, if you consider the curvature is going to be pretty complicated. It's really complicated, yeah, and you need to have lots of information from different space, and you actually have to distinguish. So you actually have to do upwinding and stuff, yeah, to get this stable. Yes, I mean, it's a pity that we never wrote a paper about this. Yeah, but it's okay. So it's not actually. Yeah, you approximate pointwise distances, but you're not really approximating the curvature. Yeah. So to be really accurate. Sorry, yeah.
Okay. One thing is that you can estimate some boundary cutting through your grid.
Yeah.
But what about the gradients? If you want to estimate the skin friction.
Yeah.
Can you estimate the gradients also on normal to your surface?
The skin friction. Okay. Now we get again the question where we can discuss for a very long time. So in principle, the boundary, that's true that this is a problem. The boundary is not part of the simulation domain. Yeah. So we don't get any information directly on the boundary. So if you want to compute the skin friction, then you have to do something else. So but a little bit the thing is, why do you want to know the skin friction in the first place? And this may now sound like a stupid question of myself. But so there is one point that you have to distinguish between. I mean, if you come from the Navier-Stokes world and you want to have forces on the boundary, then you have to integrate over, the stress, for example, and the different parts there. Yeah. So if you want to know what is the momentum exchange between the surface and the fluid, then you have to remember that you are solving for these populations. You have a kinetic solver. In this kinetic solver, the momentum is your primary. I mean, this actually is not the primary variable, but you have the microscopic velocities, yeah. And so with the microscopic velocities, you can simply calculate what amount of momentum is going through an interface. So in Lattice-Boltzmann, you do not integrate the stress because you can directly compute the momentum exchange with the surface. This is extremely simple in Lattice-Boltzmann. Yeah, this is why we don't bother that much about that we don't know the stress. Yeah. So I mean, if you now insist, so you want to have the things taken apart. So what what is the pressure value there, what is the stress there, yeah, if you want to take this apart, because this is the way you think about this in the Navier-Stokes world, then of course we are a little bit in trouble because we already get the integral. We know the integral. If we want to take it apart, then we have to, think harder. Yeah. We also have, because we were asked by Navier-Stokes guys, what is the CP value, yeah? Yeah.
You have the microscopic field, you have the velocity field, and then you can use, this is method B, I would call it, which is practical. And you would use finite differences to, you can project the velocity on the surface or a nearby surface because we don't have the surface.
Yeah.
Then you can calculate the shear stresses from there.
Yeah, so if you, right.
I would assume this won't be as accurate as the method.
And it is doing something. I mean, this is.
Sorry, yeah, sure. I don't know if I should spend time on this guy if it's not, if time is running,
Yeah, it's a pretty important thing, because if you come from the Navier-Stokes world, and also PhD students, I've observed this. So they want to, I observed this. They wanted to compute the force on the body, and I see them integrating the stress, and I say, what are you doing there? Yeah, it's not necessary. Yeah. So this is something that the students should be aware of, that this is not necessary in Lattice-Boltzmann, because you are more you're closer to the physics. You don't need to take these things apart.
But one thing is how to compute it. So another thing is, I think you also think about it. If you have something like an aerodynamic shape wind turbine blade, then the boundary layer is extremely thin.
Yeah.
And very important. And therefore, the only way you can get around it is resolving it, right? I mean.
Yes. So this is why the next point here is grid refinement. Yeah. So maybe I'll just go on and say grid refinement. Okay? So grid refinement. Okay. I try not to make it. I try not to take now forever here. I will explain grid refinement only in 2D. It works the same way in 3D, yeah, but it gets more equations. So I'll going to simplify this. So first of all, if we do grid refinement, at least if we do this in VirtualFluids, and I would say that 95% of the Lattice-Boltzmann world agrees on that point, we use acoustic scaling. Delta x is proportional to delta t, meaning that Cs is constant. So this is important for the reason that because we have this fixed speed of sound in Lattice-Boltzmann, we want to have the same speed of sound in whatever region of refinement, even if we consider the problem that we are solving as incompressible. Because the reason for this is we don't want to have any reflection. So you will know if you have a change in the propagation speed in a medium, like you look at the window, there's a difference in the propagation speed of light. Every time you have this difference, you get a reflection. This is why you see your reflection in the window, because the speed of sound, the speed of light in the glass is different from the speed of light in the air. Yeah. So there's a theory about this, Snell's law, yeah, where you can actually pretty easily compute this. So in order to avoid this, the speed of sound in all the domain need to be the same. This is why we use acoustic scaling in grid refinement. This means when we do grid refinement, we are not reducing the error in Mach number. Yeah? This can only be reduced by reducing the time step everywhere, not the grid. So for people coming from the Navier-Stokes world, this means something else, because you may not even consider it necessary that you refine the time step together with the grid spacing, because in many codes, like in CFD software, usually you have a global time step that does not care about the grid spacing. In the Lattice-Boltzmann method, it is you usually have nested grids. Yeah, so they are all Cartesian grids, and when you refine the grid, you also refine the time step. So you have a different time step on a different resolution, which has the advantage that you never run into CFL problems, yeah, because you increase the grid spacing, you also increase the time step, so you never have a CFL issue. So you can actually use large time step in the coarse grid, whereas if you think about usual finite volume schemes, then the global time step, even for the large cells, is dictated by the smallest cell that you have in your domain. And this is not the case in Lattice-Boltzmann. To avoid pressure reflections, I say probably I write at interfaces. So then there is something else that we use. Not everybody is using this, but we are using this. Is we use staggered grid refinement. Again, this is something that I could now So I could discuss this in detail. I'm not going to do this in regard of the time. This is done for avoiding aliasing. I never know how you want to pronounce this. At the downsampling. So people who study signal processing will know this. If you downsample a signal, you have to low-pass filter it before, yeah, so that it does not contain any high-frequency information. So, and if you have overlapping grids, and you would assume you can just, so if you have overlapping grids, then the coarse grids will always overlap with the fine grid, so you could believe that you could simply copy the populations from the fine grid to the coarse grid. And this was done in the beginning of grid refinement and worked very well for the examples that they show in laminar flow. But this works only if your simulation is well resolved on the coarse grid, which somehow makes the entire thing a little bit why do you want to do this? So in particular, if you have turbulent flow, this never works. Now what you can do, you can add an explicit filtering step before you do this, which has been done by the group from Geneva. But I find it a little bit, yes, I don't really, okay, I mean, you know, you're repairing something that you know would go wrong. So if you use staggered grids, then automatically you always have to interpolate, and the interpolation is a kind of low-pass filter, and you never run into this problem, and you can do this also for turbulent flow. So there are a few things that you have to consider because we are using acoustic times acoustic scaling. We have to adjust the relaxation rate. To see this, remember what is the kinematic viscosity. There is this 1/3, which is actually the square root of the speed of sound, times 1 over omega. So this is the omega of the second order moments, delta x squared divided by delta t. So this is the physical velocity, the viscosity. So obviously this implies that 1/3 on the coarse grid, omega on the coarse grid minus 1/2 delta x on the coarse grid squared by delta t on the coarse grid needs to be the same. The viscosity needs to be the same in the entire domain. 1 over omega f on the fine grid minus 1/2 delta x on the fine grid squared divided by delta t on the fine grid. So we are assuming that we always refine in each interface by a factor of 2. Yeah, this is the only thing now that we are allowing. And if we want now to compute that 1 over omega fine can now be recalculated as delta x cos squared divided by delta t c times delta t fine divided by delta x fine square into 1 over omega cos minus 1/2 plus 1/2. And because we are refining by a factor of 2, this here comes together to a factor of 2. And this means that 1 over omega f translates into 2 over omega cos minus 1/2. So this is how we have to scale the relaxation rates between the fine and the coarse grid. This also means that the non-equilibrium populations have to be scaled too. Because they are not scale invariant. This we can obtain by asymptotic analysis or simpler by Taylor expanding. So we take the moment equation that we had in lecture number 1 today, and Taylor expand it and say, now I simplify this to 2 dimensions. Yeah, MAB will find is MAB equilibrium, and the equilibrium in acoustic scaling is actually scale invariant. And then there is minus delta x divided by omega, and here we have dx m a plus 1b plus dy m a b plus 1. And all of this is the non-equilibrium part. And here, because it's a Taylor expansion, we have a reminder of delta t. And now it's actually delta x squared. So, and this is not scale. Say, it's not invariant, so I call it is scale variant. So it's depending on the scale. Okay, now come in a minute to how we are doing this, but first of all, I mean, we are going to interpolate this. Let us briefly see what are the requirements on the interpolation order. And because we are getting late, I'm doing this very hand-wavy. Yeah? Say, we just look at the Navier-Stokes equation because this is what we want to solve. And I'll simplify the Navier-Stokes equation now into a material derivative. So this is not important. I just write a material derivative here on the left-hand side. And here we have CS square into the gradient of the second order of rho, which is the pressure. I guess by dividing by rho 0. If I no, because I multiply by rho 0 on the other side. Yes. So this is a first derivative, right? So since it's a first derivative, so this is, as I said, hand waving. If we want to see the first derivative, we need at least a linear interpolation of this, right? Linear interpolation is at least required. And then we also have the actual Navier-Stokes part that distinguishes from the Euler equation, where we have the viscosity into the second Laplacian, the Laplacian on the velocity, and this is a second derivative. And this we would only capture if we have a quadratic interpolation of the velocity field. So here we would need a quadratic. Again, at least, yeah? So from this we assume that, wait, it's going to be too late. Is there a minus in front of the pressure Navier-Stokes equation? There's a minus. Okay, I see. This is apparently, I'm doing this too long today. How can't you know the Navier-Stokes equation? What are you doing? What is your job? Okay. Yeah, sorry. Okay, so we get along with one order less in the pressure term than we get in the velocity term. Yeah, and now I'm just telling you how we do this in VirtualFluids. So there we use the compact interpolation. Compact interpolation. So the idea behind this compact interpolation is if we want to have quadratic interpolation, then we use a big stencil. We need to know our neighbors. We don't like to know our neighbors. Yeah. So we try to reduce the information that we are using. So reduce the stencil size by making use of asymptotic analysis. Okay, let's just get into the methods. Let me think. I need to have 4 of them. Yeah? So, our interpretation of the Lattice-Boltzmann methods is that it's a collocation method. And you'll find for example, if this was a Valbala community, they will always talk about cells rather than points, rather than nodes. We talk about nodes. We have the analysis that we do is based on the assumption that there's a collocation method and not the integral over a cell. Yeah. So this is now going to be important because in the virtual fluids we talk about cells, interpolation cells, and they are different from the cells that are in Valbala, where a cell is the surrounding around one lattice node. In virtual fluids, a cell is the the inner part of this box where we have the nodes on the vertices. Yeah. So it's not cell-centered, but it's what is it? Node-centered. Yeah. No. It's not node-centered, it's cell-centered. Yeah. No, okay. So the cell, the Valbala would put a cell around this here. We put a cell around this here. We only use cells in interpolation. So this is our cell, and here we use this for interpolation. And this is a coarse to fine interpolation cell. And there is also a fine to coarse interpolation cell that looks like this. Fine to coarse. So the round thing we call a source node. And this thing here, the cross, is a destination node. So we interpolate the destination nodes from the source nodes. And the information that we use on the node the information at the source, so at the source node, is we are using rho for our interpolation. We are using u, velocity in x direction. We are using v, the velocity in v direction. And then we are using the second order cumulants. And of these, there in 2 dimensions, there are 2, and in 3 dimensions, there are good, but not. So how many second moments do we use for interpolation in 3 dimensions when this is compatible with 2 dimensions? So there is 2 in 2, then there would be, give me a number. So who's saying 3? Who's saying 4? Who's saying 5? Who's saying 6? Okay. So when it would be, okay, we are not using the trace. Yeah. So then it would only be 5 in 3 dimensions. It's 5. Because we are assuming incompressibility. So, I mean, we could also. Well, they are this C110, C101, C011. And then there is C200 minus C20, and then there is C200 minus C002, and not using the trace. So you're disappointed that it's not 6. It's, I mean, you can. But I mean, then you get into trouble with the order of accuracy. So I mean, okay, we are only using yes. there are 5 here. Okay, I need a new page. So, how are we going to do this? We don't want to interpolate these guys directly, but we want to have a second order. We want to have second order interpolation on these cells. Now you notice if you use these 4 nodes, yeah, you don't get a second order interpolation. You get only bilinear interpolation, or in 3 dimensions 3 linear interpolation. So in order to amend this, we use our knowledge from asymptotic analysis. And from asymptotic analysis, we know that at the second order of this cumulant C11, this is the one without a star and without an overbar, so it's the pre-collision state, is okay. I made this up on Sunday evening, so I don't know. We noticed that I make mistakes, so I hope this is. Wait. I actually made a mistake. Great. Okay. So this is the first derivative in x of the y velocity plus the first derivative of u, the x velocity in y direction. And the other thing, this 2, 0 minus C02 to second order is minus 2 to 3 omega dxu first minus dy v first order. Yeah? So this is, so you see we have information on the gradient of velocity inside these moments. And this is something that we use to amend our interpolation order. Now we need to go to second order interpolation.
It should be the first derivative in y.
Okay, so there wasn't just, this is what I meant, but I'm lecturing for pretty long now. I don't know. Maybe you get tired. I have no opportunity to getting tired here. Yeah. So we want to have second order interpolation function in velocity. So we make an ansatz. Yeah, we say that u at x and y is given as a0 plus ax times x plus ay times y plus ax y times x and y. So this is bilinear interpolation, right? So, and this is the information that you get just from the velocity itself. Now, this is not sufficient for recovering the right viscosity in the Navier-Stokes equation, so we have to amend this by axx times x squared plus ayy plus y squared. Times, yes. Sorry. Yes. Okay. I know I was, where are you? Yeah, this is, okay, no, don't. The secret. Sorry. The same thing here, so we call this now b xx plus by y plus bx y times xy, and we have to amend this by bxx times x squared plus byy times y squared. And then in addition to this, we also need the rho, and this we do, and because I want to make it compatible with what we do in virtual fluids, where we have the c for the last velocity component, and we have the pressure we call d. So we have dx plus So what am I doing? Yes, dy times x times y plus dx y x y, and this is bilinear. Actually, there is a method in VirtualFluids to also get the density interpolated in quadratic way, which needs a little bit more theory to actually get there. I'm not going to talk about this. You may find this in the code. Yeah. So there's also, we can also do this quadratically, but you know, this is higher order. Yeah? It's not in the open source code. Okay. Yes. Yeah. So there are different. Yes, maybe we have not done this in the. Okay. So anyway, then this is perfect. Okay, we are a little bit troubled here, and the same thing happens with in 3 dimensions, because we have, when we look at the information that we have 4 nodes, and on those 4 nodes we get for the velocity 4 quantities. That's we have 4 times 4 times 16 quantities, moments for velocity interpolation on 4 nodes. But the number of quantities that we have here is 1, 2, 3, 4, 5, 6 times 2 is 12, yes? So, but only 12 coefficients. That gave me a lot of headache in the beginning, because we have an over specified system. Yeah, but they are not, okay, so they don't interpolate row, yeah? So therefore, they don't help. So we need to have some data reduction, which is not a big problem because we have to low-pass filter anyway, right? So the solution that has been chosen, and there were different possibilities, but the way this is now done is we are using data reduction with a finite difference stencil with kind of an interpolated finite difference stencil. So I tried, and hopefully you'll just get what I mean. So I have a one finite difference stencil that I call, that gives us the a finite difference in y direction in the center, so they're all centered, yeah? So we do a finite difference on the left, and we do a finite difference on the right of the center, and then we interpolate the two. This interpolation has some low-pass characteristic also, yeah? And this reduces information, and then we have the same thing in x, so we have dx on something. And then we apply this something on the on C11, for example. So if we apply it to, then because we know that C11 gives us dxv plus dyu, and if we put the interpolation functions into this, what comes out is, so there's a second order polynomial. We take the second derivative, so there's a first derivative here, and then we take a first derivative again. What drops out of this is 2 times bxx plus axy. We have d, then we apply dy onto the same thing, dxv plus dyu gives us bxy plus ayy. Then we do the same thing for C20 minus C02, and dx So what is in there? There is the first derivative dxu minus dy u, and if you apply this to the polynomial, then we get 2axx minus bxy, yes, dy dxu minus dy u is equal to ax y minus 2b byy. Okay, now we have reduced our data. What we take everything else, all the other coefficients we get simply from interpolate from the velocity on the nodes. So then what you do is you can solve this. Unfortunately, in particular in 3 dimensions, is not very beautiful. You solve the system for the coefficients. Then you measure these quantities, you compute the coefficients, and then from the coefficients you can do the interpolation. Yeah, so you apply this in interpolation. To get the macroscopic quantities from which you can compute the equilibrium, and you can also get the non-equilibrium. The non-equilibrium populations from the derivatives of the interpolation function. Now remember, the non-equilibrium that plays a role to the leading order is the C11 and the C20 minus C02. Their equilibrium would be 0, right? So these things are related to these derivative in velocity. Now you have an interpolation polynomial. You can compute from the interpolation polynomial what is dxv plus dyu at this position. Yeah, you can compute this and then set this non-equilibrium cumulants to that particular value. Yeah, so that you recover them. Then there is in virtual fluids one particular boundary case. Boundary case, which is actually a boundary. Okay, I'm going to be very brief here. So suppose you are in the trouble that you actually have a boundary. Okay, I'll draw it a little bit smaller here. So this is your coarse grid, and say we have a fine grid in between, and you have your grid interface directly cutting into a boundary. So then these things, maybe I draw them in a different color. So you would like to know, you would like to interpolate these red nodes. So say these are the destination nodes. Now you are troubled insofar as you don't have a full cell here. Yeah, the other nodes are inside the solid. Now you could say inside the solid they have velocity 0, but this doesn't make sense because there's a discontinuity in between. Yeah, so you can't use this. So what you could use is the velocity at the boundary here, but this is going to be complicated. So the very simple solution, and maybe that's not extremely accurate, but the very simple solution that is taken in virtual fluids is to use an offset. And maybe that's not the best idea in the entire world. And I was very skeptical about this and was amazed that it's actually stable, because all we do is we use the next nearest complete cell and evaluate the interpolation function outside. And I noticed this works because we always do this towards the wall, right? Towards velocity 0. Yeah? And though there is, because this could obviously be unstable, but because we are going towards 0 velocity, this is actually observed to be stable. So this here is our source cell. There's just so what we are doing here is a simple extrapolation. Where we have UBC for the wall, UBC is equal to 0. This apparently works. Okay, last page. Algorithm. Okay, still I need to draw something. Now say we have a fine domain on the left side and we have a coarse domain on the right side. Then have this like this and say there's a coarse node here and a coarse node there. And these here are my interpolation cells. And so the fine grid has some overlap with a coarse node here. Duck, 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 duck. Right. So this actually will be, then we put an interpolation cell here. So this is actually the last line of fine grid nodes, and this here is the last line on coarse grid nodes. Yeah, and we have this finite overlap here. So now this is, we are assuming that all these nodes are valid, and what we call now step 1, all nodes are in a known state. What I'm going to do is I'm copying this around. I'm copying this around to go to the next step. Maybe, wait, I should do this in a different way. Just copy this. And I paste it like this. So, okay, so this gives us, where are we? Step 2. So step 2 is we do a fine time step. Now remember, we have nested time steps. We have 2 fine time steps for 1 coarse time step. If we apply 1 time step, we do a collision, we do a streaming, then you notice that these nodes here on this side, they don't have any neighbors on one side. So they don't get information coming in from the right, meaning after the streaming, they will be invalidated. Yeah, we don't know their state anymore. Okay, so this is step number 2. Comes step number 3. step 3, we have another find time step. So the second row that we have here is now no valid neighbor, so we'll get these things get lost, right? So they become invalid. Then we go on and take this again. And go to time step number 4. We do a course time step. So after we do a course time step, remember these course nodes here have no neighbors to their left, so they will become invalid too. So now we have lost all of them, and we have done 2 find time steps and 1 course time step. Then after this, there is actually time for synchronization. And now let me copy this here again. So in this last step, in this last step, what we are doing is, oops, what is happening? In this last step, we are doing the interpolation in these interpolation cells. So we put them to green. So this is step number 5. Now we synchronize. We do the interpolation we do all the interpolations at once. All the interface nodes. And then we again have valid situation, and we go back to step 1. So, I mean, sometimes we get some complaints that this is not the best grid refinement in the entire universe, but it is relatively simple in a way that it requires no interpolation in time. We have this overlap, but then it requires no more interpolation. And another thing is that this distinguishes it from some other method, that it does not use any special treatment for corners and edges. We always have these cells that we interpolate, where we take the source nodes and we interpolate to destination nodes. Yeah, so this is the same on the corner, on an edge. Yeah, always behaves the same. So this is the way it is done in VirtualFluids, and this is now actually what I had for today. I'm amazed I did everything that I prepared. So how much overtime are we? I guess I'm stopping the recording.